Thank you very much. So I will present some more applied research, very recent research results, which we obtained within our complex group. Sheng Feng was a former postdoc from China. István Pak was also working with us. External collaborators, Gustavo Deco, who is in Barcelona as head of the cognition and brain sciences, and Jeffrey Kelling, who provided us this fantastic CUDA implemented ordinary differential solvers, which we used. Okay. So, as the title shows, I will speak a little bit about critical brain hypothesis, which is based on some early experiment back to 2003. And later on, it was confirmed by some other experiments, and some theories also provide very strong motivation. Although, as far as I agreed, I see that not everyone in the neuroscience community shares this critical brain hypothesis. We will try to show some simulations on some full brain models. So one fact is that neurons exhibit oscillatory behavior, and the question is, can we see criticality and synchronization together in these brain models, and whether they can be compared with some measurements, experimental data. Just to remind you very quickly about this criticality, because I assume that not everybody in the audience is a physicist, and just coming back to the secondary school knowledge about the phase diagram of the water, there is a critical point on the pressure temperature line at the top right. Beyond that, there are first order transition separating different phases, but at this end point, there is a so-called second order or continuous transitions, and it's a very special point because there are very strong fluctuations, diverging correlations, the correlation length and time diverge, and there is a rescaling invariance in the system. That means that system functions are homogeneously, can be rescaled. And this involves different power laws, for example, in the specific heat, the fluctuation as you approach the critical point. All of them shows this special behavior, which is sometimes universal. There are universality classes. And now let's see what is observed in brain experiments. This is the 2003 electrode brain experiment, which was done by high density array of electrodes displaced on the human brain, and spontaneous avalanches are measured. You see it is a log-log scale, so the straight lines corresponds to power loss for some decades. And this was confirmed for humans and animals in vitro. And there were other experiments, fMRI bold experiments, volume image calcium, and so on. And another interesting is the long-range temporal correlation experiment, which are not such a fine grain, which you see, but measurements on the MEG and EEG signals where this kind of power law correlations could be found, and the exponents related to them are summarized in the table here in the task phase and the rest phase of the brain. Okay, so this shows some universal exponents. Question is whether they are mean field or non-mean field like. And another question is, thank you very much. Why would the brain be critical? So some advantages that thanks to the diverging fluctuations, there is a high sensitivity to stimulus in such kind of systems. And also due to the diverging correlation functions, there is an optimal transmission and storage of information because you don't need to wire very distant parts of the brain, but information is traveling through these long-range correlations which emerge. Okay, and there is also a maximal information processing and computational performance in brain system, which was shown, and this opens up the question is that in artificial intelligence, this could be also explored, and I also heard some studies which was really showed that for example, in reservoir computers are really optimal if they are tuned to this edge of criticality somehow. So the critical point has an advantage and disadvantage. Just the disadvantage is that you need to tune. It's a special point. And there is another one is there is a danger of being supercritical, which is in a human brain means epileptic behavior, but there are models to tackle it. For example, self-organized critical model, when due to the learning and plasticity, the system can tune themselves close to this point. So let me go to the whole brain simulation. We took the simplest model first, coming from 1975. This is the so-called Kuramoto oscillator model. It's just a 50 years old model where you have phases, theta I, which are coupled by this sine function. And there is also a global coupling in the system, which is our control parameter. And local coupling between the nodes is characterized with this WHG adjacency matrix. And note that also in the equation, you have this omega I0, which are some self-frequencies, which are quenched random variables chosen from uniform Gaussian distributions. And usually we measure this R, capital R, which is the Kuramoto order parameter, which is the sum of the phases normalized. And this order parameter changes when we vary K, the global coupling. Sorry, the lines are looking a little bit mixed, not on my PDF version. So in principle, for K is less than Kc, the system evolves to a very small synchronization characterized by this R value. So if the n, the number of nodes is large, it goes away as 1 over n to the power of 1/2. And if you are in a large coupling regime, then the system will synchronize, but in between there is a critical point at Kc when you can find scaling laws, which is shown here by these equations. So the R can grow as t to the power of eta. And we know many things about this simple model. It has a critical transition for d greater than 4 spatial dimensions. It suffers very strong corrections to scaling and chaoticity. So we will use this toy synchronization model first, assuming universality, because we know that brain is not such a simple toy model, but let's see first. So we solve this coupled set of nonlinear ordinary differential equations. The difficulty is that if you want to have a whole brain model, you have at least 100,000 nodes in fly brain with millions of edges, and we have to repeat the solution for thousands of realizations corresponding to different cell frequencies. We didn't use the stochastic noise node that we only have chaotic noise. And now the GPU part, which is cannot be seen very well on this text, we use the Jeffrey's CUDA algorithm, which is a VexCL and boost library program and can achieve a speed up of 100 with respect to the corresponding CPU codes. So just to summarize, we measure this Kuramoto order parameter, which I mentioned to you. We can also measure the frequency variances and local synchronization measures, not averaging over for all neighbors, but the neighboring systems. And finally, we measure the autocorrelation via the standard Hurst and beta exponent analysis. So this kind of numerics was implemented on the HPC machines. Earlier, we ran it on Barcelona supercomputer, recently on the Commodore, and we want to express gratefulness. So thank you. So time is running very quickly. Just for the results, I show you the fruit fly recent one, 21,000 nodes and 3 million edges with certain weight distributions. I cannot go into the detail, and we compared it to the fully random Erdős-Rényi graph and determined the evolution of this order parameter, which can be seen on the graph, and the critical point by the local slope analysis, which turned out to be a non-mean field one. And then we moved one step further. We added to the Kuramoto this external force, which is a periodic noise, external force and the noise, okay? And as you can see in the snapshots on the local parameters, with no force for, this is the first line is for earlier time step, it is a later time step, and the color coding shows there is not too much ordering in the system, but if you allow this force to be greater than 0, this will turn into the green one. So this corresponds to the ordering, and this was measured here on this graph. The red point shows the Kuramoto order parameter as the function of this force. It grows towards a synchronization, and the transition, you have some standard deviation peaks. And we also compare these peaks for different forces and couplings. And one of the most interesting result is this fluctuation corresponding to sensitivity is maximal just for the F0, so to the resting state. Kuramoto just at the critical point, as I told you. And so this was also measured on this Hurst and beta parameter for communities determined of the fruit fly. So you see community dependencies of the autocorrelations, and you have the largest deviations from the 0.5 for the no force case, again, here, these black ones. And this was also repeated for a human brain connectome, very similar, but much larger number of community. And here is the comparison with the fMRI measurement from this Polish group published in scientific reports. Again, you see the community dependence of the Hurst and beta exponents. The black is the resting state, this is the highest, close to 1, and so on. I cannot go into detailed discussion since my time is out. Just a few more sentences about the second part, about this fluctuation dissipation. The brain is, of course, is a non-equilibrium system, and you can measure this level of non-equilibriumness by the so-called fluctuation dissipation, which is based on the comparison of the autocorrelation, the auto-responses for some external noises. And we did it at the critical point when both the A and R shows scaling in the long time. And here is this famous fluctuation dissipation. So the response function should be proportional to the the start time derivative of the A's. And in equilibrium system, this is just a constant. But if it is not a constant, we see the violation. And we compare this for different anisotropies on the weights of the brain connectomes, and measure the response and the phase response and phase correlators here in the system. And here is the results for the autocorrelation. Is the function of T over S. It has some large fluctuations. But if you make a absolute value, because it goes to negative on the log plot, you can see some power law like tails. So it's very difficult to analyze. The response function is better. There are no such big fluctuations, and for different initial time, S times, you can get a nice scaling collapse. And now you can calculate this dA derivative dA over ds, which due to the large autocorrelation fluctuation is difficult to measure, but for different anisotropy scenarios here, we can prove that the more anisotrope the system, the farther away we are from the criticality. So just to conclude, the autocorrelation suffered from large oscillations. Still, some power law could be fitted. Autoresponses exhibit nice scaling collapses, and the physical aging exponents are obtained. The violation measure follows the sequence of anisotropy. The sensitivity is maximal in the resting state of the brain. Hurst and beta exponents are community dependent in agreement with the fMRI measurements qualitatively. So we are a bit happy that even our Shinamoto-Kuramoto toy model is a kind of qualitatively good synchron model of this brain measurement. And there's some nice possibility to predict clinical data based on this good agreement with fMRI measurements. And if you want to see some results, we have 2 papers with the authors I mentioned. One of them is in Frontiers in Physics, and another is just still a preprint, is under review. And I would like to thank you for your attention, and again, grateful for using the Commodore and the hardware in Hungary.
Thank you very much, Géza. Questions?
Thank you very much for this presentation. It's very stimulating, inspiring. And so my question is whether the 2 different connectomes, the fruit fly and the human brain, differed in terms of directionality, whether the network you used were a directed network or undirected network.
So the fruit fly is a fully directed network. It's a neural level, and the human brain is a non-directed, because this is coming from this diffusion tracking measurement, so it is a non-directed. But we did not apply this second part, this fluctuation dissipation for the human brain.
So these are network level representations, but at very different scales. Because in the human brain, the network includes thousands or maybe more neurons,
Yes.
tens of thousands of neurons, and the connectivity between them in both directions. Whereas in the fruit flies, the connectivity is at the neuronal level.
Yes.
Did you see any difference in the dynamics of these two?
Well, I mean, you know, we considered these connectomes as just as close systems to reality which can be obtained nowadays. And of course, there are some differences on the dynamics, but for statistical physicists, it is coming from the spectral dimension, the modularity, and so on. So let's say yeah. I mean, the human connectome dimension seemed to be somewhat lower than the fruit fly for some reason, but maybe it is also the fMRI artifact which might have omitted some long links. It is known that it is not a perfect one. So since it has a lower dimension, its synchronizability is lower as well.
Okay, one short. No, okay, so then we are short. Make it 12.
So from what I saw from the chromatin model, it seemed very much like inverse Fourier transformation, because it's basically you're like adding a bunch of like sine waves together, right? So I was thinking because it's basically an inverse Fourier transformation, it would be like, since the Fourier transformation is differentiable, I was thinking like maybe the inverse would probably also be differentiable, and that would also imply that you could basically train the weights matrix, right? Because you can obtain some kind of difference, because you can get basic compute the gradient from your different outputs because it's differentiable. But I was like, is that so you can get like I don't know how to explain it. So because the signal that you're computing, right? It's like like the chromatin model is like adding a bunch of sine waves together, right?
I don't
Okay.
Sorry. Sorry.
Maybe we can leave this for the lunch time. So thank you very much, Géza, again.